Hello and welcome to College Physics 2, Lecture 8, Electric Potential and Conservation of Energy. This lecture is part 2 of 3 in our discussion of the concept of electric potential. Here we're going to focus more on the energy side of things and kind of quantify or come up with a way to describe all of this mathematically. But to start, let's take a step back. Let's revisit the concept of the electric field because this all has kind of a interconnectedness that we'll bring together starting in this lecture and going into the next. To visualize an electric field can be difficult because it's invisible. Even though there's an electric field around all of us right now, we can't really feel or see it. So a lot of times analogies will be useful to visualize these things. So to visualize an electric field, consider a large horizontal sheet that is pulled tight. Perhaps like a spandex material that's pulled tight. That sheet represents space, with no charges, let's say. So now imagine placing something heavy in the middle of that, like a billiard or pool ball. Well, if you do that, the fact that the ball is now on the sheet is going to cause it to warp. Right? It's going to cause it to sag in the middle where the ball is located. In other words, it's going to disturb that space. Well, that ball disturbing the fabric is the same as an electric charge disturbing the space around it. So just imagine that the billiard ball at the center is this, say, negative charge, and then the fabric is the space around it. It is altering the space. So let's just imagine that we then place a marble on this sheet, and that represents, say, the opposite charge. So in this case, in my example, a positive charge. Well, if you let go of that marble, the space around it is altered already because of that negative source charge in the middle, and so that positive charge is going to start accelerating down toward the billiard ball because they're attracted toward one another in this case, right? Opposites attract. So this analogy kind of shows us what's happening. Even though this isn't 100%, a perfect analogy, it does at least let you visualize it. You see the big negative charge or the source charge influencing the space around it, and thus the probe charge or the test charge, represented by the positive sign, being affected by that and seeing an attraction. Now, that's only true of opposite charges. If you want to imagine repulsion, you can basically do the opposite. Instead of having a ball sagging the fabric downward, just use something like a pole pushed up into the fabric so that it is raised in some area. So now imagine that's a positive charge instead. Well, now you take another positive charge or a marble on that material, you let go of it, and it's going to accelerate down and away from the center where the positive charge is. So this is like charges repelling one another, right? So these two visual analogies kind of allow you to, just get a better idea of what's happening in the space around charges. They're not my most perfect drawings ever, but I did what I could. So hopefully that at least allows you to visualize this a little bit better. Now, with that said, we can hop back into our discussion of potential because just like a charge will create an electric field everywhere in space, it also creates electric potential everywhere in space. So let us continue that discussion. So we introduced the concept of potential and potential energy in our previous lecture. So let's just kind of summarize that material here. There is an equation that relates the two, and they sound so similar that they are, of course, related. So the potential energy, which we denote U, ELEC, is equal to the charge Q times the potential V. So the equation is U equals QV. So there is a very close similarity between the two, but they are different. A basic definition of each is presented. We say that the electric potential energy refers to the energy associated with a particular amount of charge at some position. And we measure energy in joules. Now, on the other hand, which might be the harder one to understand, is electric potential, and it's a very similar definition. It is the energy associated with a unit charge at that position. But the big difference is this. It is always there whether there's a charged particle there to experience it. So if you think about the equation we have on the screen and we rewrite it for potential, you will see that V is equal to U over Q. So by definition, our potential V is equal to the energy per charge. So that's the only difference, is it's the amount of energy present per charge. But it does not depend on what charge is there to experience it. This is automatically there. This potential is already there, and then other charges just come in to experience that. And so if you look at this equation, the units are energy measured in joules over charge measured in coulombs. So that is a unit of a joule per coulomb, which we call a volt. Right, so this is all recap from last time. Well, let us introduce some new things here. First, let's try to make another analogy. This is one of the only drawings I've ever actually spent time on. I never saw a really good cartoon depicting this analogy, so I figured I'd make one. So let's just say, if we want to have a better analogy of this concept of potential energy, let's think about a waterfall. So think about a water molecule, just a single little drop of water, as it falls down the waterfall. Think all the way back to physics 1, what that would mean in terms of its energy. Starting at the top, it might be flowing horizontally, through a river or a stream. But then when it gets to the top of this waterfall, it starts to move downward. Well, when it's at the top, right, it has a lot of gravitational potential energy, right? So at the top, we have a lot of gravitational potential energy because it's the energy associated with height above the ground. So when we're up here, we have a lot of gravitational potential energy. But as that water molecule falls down the waterfall, it's getting closer and closer to the ground. As a result, it is losing that gravitational potential energy. Right? This is all from physics 1. So any object that is moving closer and closer to the surface is losing its potential energy. And when it's on the surface, or the lowest level in this case, then it would have no gravitational potential energy. So as this thing falls down, it's losing that potential. But energy has to be conserved, remember. It doesn't just go away, it has to go somewhere. So think about what that molecule does then. As it falls, it picks up speed, right? It starts moving more quickly. In other words, it's gaining kinetic energy, right? Kinetic energy is the energy of motion. So as it falls down, its energy is being transformed from potential energy when it's way up high and moving very slowly to kinetic energy when it's down low, moving faster. So this is exactly what happens when a charge is in an electric field. The electric field, E, is like our waterfall, let's say pointing from top to bottom. Well, instead of a waterfall and a water molecule, how about an electric field and an electric charge? The electric field points downward just like the waterfall, and so if we release this positive charge, it's going to move down the waterfall or move down the electric field. Well, the same concepts apply. It will be moving from a region of high potential energy to a region of low potential energy. So this is showing us that, the electric field, E, if you look at this, it's pointing from high potential energy down to low potential energy. So the electric field points from high to low potential energy, which means for a positive charge, it is going to gain kinetic energy because of conservation. And so our charged particle is going to speed up. So if you ever need to think about what a charge is doing, whether it's going to gain or lose a certain type of energy, or if it's going to pick up speed or slow down, maybe just think about the waterfall. It's such a helpful analogy for a pretty complicated and confusing concept. So again, just look at our waterfall here. Just imagine this is a positive charge in an electric field. Our waterfall is that electric field, right? So it's moving from high potential to low potential, so it's picking up speed. So exact same idea. So hopefully that connection sits well with you. That is the single analogy or idea that really helped me personally understand this concept when I was still learning it. And so I hope that same information is helpful to you. Okay. Well, there is a way to mathematically describe this too, so we can prove all of this with equations. And so we'll do that. If you recall from Physics 1, we had a very large conservation of energy equation toward the end of the course. It looked something like the following. It looked like K final plus, let me think, we had plus UG final plus US final plus, I believe we also included delta ETH, and then equaled all the initials. So K initial, UG initial, and US initial. This was our conservation of energy equation back from Physics 1. Right, so this is an old equation that we had to use back in the day so that we could determine certain types of energy or how fast a molecule is moving or something. So this equation says that you have conservation. Whatever you have initially equals whatever you have finally, where K is kinetic energy, UG was gravitational potential energy, US was spring potential energy, and ETH is thermal energy. So these are all energies we were dealing with in Physics 1. But think about what we're talking about now in Physics 2. Gravitational potential energy means an object moving up or down, essentially. Well, we're not really talking about charges necessarily flying up or down through space. So there's not really any gravitational potential energy that we have to worry about. US is spring potential energy, if you're compressing or expanding a spring. Well, we're not dealing with springs when we're talking about charges. Thermal energy was present whenever there was friction generated between two objects that are rubbing together. Again, here we're talking about charges, not objects rubbing together. So none of those energies are really necessary for us to discuss here in Physics 2. The only energies we really have to worry about, at least in our basic sense, is the kinetic energy, the energy of motion, because charges do move, and the electric potential energy, UELEC. That's it. So the good news is, even though we have to deal with a conservation of energy problem and equation, it's actually simpler than it was in Physics 1, because there's less energies present in our systems. So, assuming there's no external forces, in other words, no work being done, the equation is simply K final plus U final equals K initial plus U initial. Or, using the equation that we had from our previous discussion, you can swap out the electric potential energy U for QV. So I marked the most important form of this equation in green to highlight its importance. Keep in mind that the kinetic energy term K does have its own equation from Physics 1, and that's 1/2 m, which is the mass, times v, the speed, squared. Well, this equation can actually be written in a more compact way, using delta symbols that represent change. So take that equation and rewrite it. So I'm going to show you the process and how we get this new equation, so I'll just do that here. We had K final plus QV final equals K initial plus QV initial. So first of all, we know that delta means final minus initial. So let me subtract K initial over to the left-hand side to give me delta K. All right, so I subtracted K initial over to the other side. Let me write this out in full so that you can see the entire process. So without using delta symbols yet, let me just show all of it. K final minus K initial, so I'm subtracting Ki over. And then let's do the same here. Let's subtract QV final over to the right-hand side. So we have QV initial minus QV final. Okay, well, remember delta means final minus initial. So that just becomes delta K on the left-hand side. And we have the interesting situation of what's happening here on the right-hand side. Notice it's initial minus final. Well, let's just reverse this. let's say, well, I want to make it a delta symbol, so I need this to be final minus initial. Basically, just swap what's positive and what's negative. Throw in a minus sign here, and that gives you minus q, and then your delta v. So that's where this equation here is coming from. Not important. Note to my personal students that you do not have to derive equations in my basic course. I just expect you to be able to apply them in certain problems. So you might need to apply this equation, but I won't ask you to go through the steps of deriving it. So this equation tells us a lot of really interesting things. And in fact, this is the equation that proves our waterfall analogy. So let's think about that. Let's think about a particle that is speeding up. Okay, so we have a speeding up particle, which means this is positive, right? Delta K is positive. Final minus initial. To be positive means your final kinetic energy is greater than your initial. In order for this to be positive, though, something interesting has to happen. Because there's a minus sign here, something has to happen to turn that into a positive. Which means we must either have a negative charge or a negative potential difference. So, if we have a positive charge, let's say, that means our potential difference must be negative. In other words, that means we're moving from a higher to a lower potential. Right? Because delta V means V final minus V initial. So we must be moving from a higher potential, initially a bigger number, to a lower potential in the final stage. So that you have a small number minus a big number, giving you an overall negative answer. That negative times this negative gives you your positive delta K. So this is the proof of the waterfall analogy. It's telling us that if we move from a higher to a lower potential, we will speed up. And that is exactly what we saw with our waterfall analogy. You move from a higher potential up at the top of the waterfall, down to a lower potential at the bottom of the waterfall, and as a result, you pick up speed. That is what this equation tells us. And I just realized I've scribbled all over the screen at this point, but hopefully that makes sense to you. We'll clean up this part. Okay. Well, the last thing to introduce before we work on two examples is the fact that we have a new unit that we can introduce here. I'm not going to really go through much of the description on this screen. I just kind of have it up as a reference, just to introduce this new unit so you can see where it comes from. But the idea is that sometimes we have energies that are really, really small. So small that the unit of a joule that we normally use for energy is simply too big. It's not a small enough number for us to really be using for, individual charges, electrons or protons. So the idea here is that we introduce a new unit called the electron volt. The electron volt, based on, the process I give on this screen, is 1.6 times 10 to the minus 19 joules. So that is your conversion factor. 1 electron volt is 1.6 times 10 to the minus 19 joules. We won't always use that unit, but just in case you have to, if a problem asks for an electron volt specifically, or if you're given a number in electron volts, you now know how to convert between the two. Keep in mind, though, we do typically need to use joules in our equations because anything we deal with in our equations uses joules. So let's take a look at an example where we have to deal with this conversion. So I'm purposely giving you a simpler example that has this conversion involved. So let's jump into it. Example 1, very basic problem. It just says, what is the speed of an 8.7 MeV proton? Now, keep in mind, M is a prefix. That means mega. So this is an 8.7 mega electron volt proton. Okay, well, we're basically given the object's kinetic energy, K. Right? We're told that it's moving with this amount of energy. Right? Electron volts is an energy. So it's given as 8.7 mega electron volts. Well, mega is a prefix which means million, or 10 to the 6. So this is the same as saying 8.7 times 10 to the 6th electron volts. Now we have a conversion factor between electron volts and joules that we introduced on the previous slide. For every 1 electron volt, we saw that there was 1.6 times 10 to the minus 19 joules of energy. Our electron volt units cancel out, giving us 1.39 times 10 to the minus 12 joules. So we have the energy now converted to joules. So we took the prefix mega into account and then converted our units from electron volts EV to joules J. All right. Well, with this, we need to figure out the speed. Well, good news is we have an equation that directly relates kinetic energy to speed. In fact, it's a physics 1 equation that I introduced again on the previous slide, or 2 slides ago maybe. So the idea is that the kinetic energy is 1/2 m times the mass v the speed squared. So if we wanted to solve this for our speed, v, we simply rearrange that equation. We have 2 times k, that gets rid of the 1/2, divided by m, and then take the square root to get rid of the square. So we have the square root of 2k over m. We can plug in these numbers. We have 2 times the kinetic energy that we just found in joules, 1.39 times 10 to the minus 12. And we have the mass. Now note, the mass is not explicitly given to us, but we do know what the object is. It is a proton. Protons have a standard mass that we know, or if you don't have it memorized, it is on formula sheets that I give in my class. Otherwise, if you're just watching randomly on YouTube, look it up, right? The mass of an electron is something you can find simply on Google. But that value is approximately 1.67 times 10 to the minus 27 kilograms. Plugging all of these values in, we will see an answer of 4.1 times 10 to the 7 meters per second. Now, that does seem quite fast, because it is. The speed of light, just for reference, which is c, we use the letter c to denote that, that's 3 times 10 to the 8 meters per second. So this is what, more than 10% the speed of light. But we're talking about a single proton, and that is possible. So even though it seems like an impossibly large number, it's not quite impossible because it's still within the realms of reality in that it's moving slower than the speed of light. And again, this might sound crazy that it can move that fast, but just think about charges in your wires of your home. You flip a light switch on, and maybe 20 feet away, a light comes on instantly. So just think about how fast the charges have to be moving for that to happen. Anyways, let's work on example 2. This one is a lot more involved. This is going to apply our full conservation of energy equation, which we saw was K final plus plus QV final equals the initial terms. So K final plus QV final equals K initial plus QV initial. The problem says that a proton moves through an electric potential. The speed is given at some point where the potential is 1500 volts. So then it asks what will be its speed a short time later when it reaches a different point where the potential is negative 500 volts. And you can see the information of this, or the context of this problem given in the image on the right. This is a rare, well, sort of rare situation here, where we don't actually have anything that's equal to 0. If you recall from Physics 1, when we dealt with conservation of energy problems, there was almost always one of these terms that was equal to 0, because the object would come to a rest, or start at rest, or something like that. But in this case, it's moving the entire time, and there's a potential the entire way, We're going from 1500 to negative 500. So nothing is equal to 0 here, which means, unfortunately, we're going to end up with a pretty ugly equation. To start, though, we have to understand what it's asking for and how to get there. It's asking about the speed. Well, looking at our equation, there is no speed in this equation as written. Be careful, this is a capital V for potential, not lowercase v for speed. So we have kinetic energy, charge, potential energy, but no speed anywhere explicitly shown. So either we're not using the right equation, or it's embedded inside of this. And it is. Because remember, kinetic energy is the energy of motion, and the equation for it is 1/2 mv squared, where v is the speed. So what we need to do is rearrange this equation for the final kinetic energy so we can figure out its final speed. So let's start there. Let's rearrange this for k final. Well, to do that, subtract your qv final to the other side. So that gives us ki plus qvi minus qv final. All right, so we're getting there. We've at least gotten it rearranged the way we need. But the problem is, we still don't have a speed shown, because kinetic energy has its own equation, 1/2 mv squared. So we need to take this into account as well. So I'm going to leave the two potential terms the same, qv initial minus qv final. But we had to expand our kinetic energy terms. Well, we're almost at what we need. We're looking for the final speed of the proton, v final. So we just need to do a little bit more rearranging to get there. First of all, to get rid of the 1/2 on the left, multiply everything by 2. And then divide by m to get rid of the mass. And then take the square root. So I'm going to start by multiplying everything by 2. That's going to give us mv initial squared, but then I'm dividing by m. So that leaves behind only v initial squared. Plus, well, we need to multiply by 2 here to each of these terms. So we have a 2. Both of them have a q in them, so 2q. And then we have v initial minus v final. And all of this, the entire thing here, is getting divided by the mass. And then we take the final step of a square root over everything. So this is probably the least fun equation we've seen in some time. It took quite a few steps to get here, but again, there's just a few steps that I took. I multiplied by 2, so times 2. I then divided by the mass, and then take the square root. So those are the 3 steps we did kind of in one here. If you aren't familiar or comfortable with rearranging equations like this yet, you got to practice it, right? It really does just come with time. And if you need to write each step out in one row at a time, you can do that, right? Multiply everything by 2 and write your new equation. Then divide by m and write your equation again. Then take the square root. Sometimes it helps to, even though it takes more time, write out the entire thing. But anyways, at this point, we can actually plug in our numbers. We do have all of this information, so let's do that. We have v initial, the initial speed, and my v's all look the same. It's kind of tough, so let me make my potential v's have like little arms at the top here. So the initial here is speed, so this is the 2.5 times 10 to the 5 given in the problem. And that's meters per second, quantity squared. Plus 2 times the charge q. Now notice again we are not given a charge in the problem. However, we are told what the object is again. It's a proton. As we saw in the last example and last lecture, and probably a few before that even, the charge on an electron or a proton is the fundamental charge, 1.6 times 10 to the negative 19 coulombs. And then we have the potential difference, but it's initial minus final, so be very careful. Initially, it was 1500. That would be volts, minus a negative 500 volts. Which order you put those in significantly matters, because otherwise we would have ended up with a negative value if I reversed them, and you can't take the square root of a negative number. So be careful about what order you put them in. And then, oops, that gets divided by the mass. Get rid of that line there. The right-hand side of this gets divided by the mass m. Now this is the mass on a proton again, which we just saw was 1.67 times 10 to the minus 27 kilograms. That is a lot of stuff to plug into your calculators, and it's easy to put in the wrong sign or parenthesis or something. So just be careful as you do this, and you should get an answer of roughly 6.7 times 10 to the 5 meters per second. All right. So there are our two examples. Let us conclude this lecture with two more basic, all things considered, end of lecture questions. Question number 1. If a positive charge is released from rest, it moves in the direction of what? All right, well, this is our waterfall analogy. It's a positive charge being released. It's going to move toward the lower potential. The answer is D. Just like our waterfall, think of the water falling down from high to low. Our charges, positive charges, are also going to move from high to low by law. So in this case, that would mean if it's moving to lower electric potential, it must be gaining kinetic energy. So it would be picking up speed as it did this, as water molecules do as they fall over a waterfall. So again, just think of that analogy. A positive charge is going to move from high to low electric potential. Well, let's take this one step further with another question, and this is actually going to be one that segues us into our next lecture, the third part of this three-part lecture on electric potential. This one says a positive charge moves as shown. Its kinetic energy is doing what? Increasing, decreasing, or remaining the same? Okay. Well, first thing we need to realize is which direction the electric field points. By definition, electric fields point from positive to negative. I'm only going to draw a few, and I am very bad at drawing straight lines, apparently. So just imagine they're straight, as they should be. So our electric field always, by definition, points from positive to negative. So this thing is actually pointing against our electric field. In other words, it's moving against our waterfall. Right? Think of our waterfall analogy again. So waterfall going down, electric field going down. So what we're basically seeing is a charge moving against our waterfall. So it's moving then from an area of low electric potential to an area of high electric potential, right? It's like a fish going up, a salmon swimming up a waterfall, right? It's going against the grain here. So we're going from a region of low to high electric potential. So if it's gaining electric potential energy, energy has to be conserved. So if it's gaining one type of energy, it must be losing another. It is losing its kinetic energy or slowing down. So that makes sense. Basically, just think of like throwing an object upward against the waterfall, right? It's going to slow down and then get pushed back down on its own. So the answer is C in this one. All right. Well, that's it for part 2. Thanks for watching and have a great day.